we're trying to solve the simulation problem through linearization, the Laplace transform, and inverse Laplace transform, right? Yesterday, we spent our time thinking about the standard input signals and how we would be able to use those standard input signals to model just about any input signal. So we don't have to, every single time, rework the entire Laplace transform of an arbitrary input signal. We can basically construct any piecewise linear function. So this is, if I have a piecewise linear function, that means I am allowed to have discontinuities. So if I zoom in far enough, basically any signal is approximately piecewise linear. So because you may be thinking, but wait a minute, Carl, what about interesting signals like slopey things that change gradually, right? And actually, when you think about it, at some level of detail, if I start approximating this by a couple of straight lines, how much of an error am I really making? And so remember, our whole approach in this subject, and especially in this section, is to do approximations right up front, right? So we've approximated the equations. We're also, in many cases, going to be approximating the input signals. And the reason why we're doing that is because we want to make the downstream math a lot simpler. And so it's this general approach that we're going to be following where we're saying, is there a way that I can simplify this problem up front and then shoehorn it into this really powerful set of theories that I'm going to be talking about today, which is all about understanding how basic systems respond to these basic input signals. And part of what we're going to be learning, and you'll hear me kind of say this as a refrain. You'll see this many, many times. Every time I take one of these approximations, I'm going to be constructing a signal as a linear combination of shifted versions of other signals, right? So lots and lots of those kinds of signals. And you'll see this pattern many, many times because, and don't be confused, let me just make sure that's like a different symbol. It doesn't have to be the same symbol. This pattern is the pattern of linear combinations. And the kind of larger word for the approach that we're going to be taking in this subject, basically for the rest of the subject, we're going to be mostly ignoring the nonlinear models that we built in study theme 1 and focusing very strongly on linear systems theory. Now, as we move away from the input signals, the next phase is to understand, so remember, we're moving in this direction. We're going, I want to know the Laplace transform of the input signal. I want to know the Laplace transform of the system, and then I want to be able to predict things about the output. The straightforward application of theory is to multiply the Laplace transform that we calculated yesterday, right? So decompose the signal into known input signals, use the known Laplace transforms that describe y of s to get to y of s, take the Laplace transform of the equations that describe the system and rearrange that into a transfer function, and then kind of multiply and invert the Laplace transform. That's the one version that we're going to do with analytic math. The other thing that we're going to achieve is we're going to be able to reason about the behavior of G even without doing the inverse Laplace transform. Because we'll see some patterns emerge where just looking at the transfer function gives us information about how that system will respond. And I want you to keep in mind that there are, if you're thinking about like an exam question, there are two versions of this answer. The one is a calculation, and the other one is something like a sketch or intuition. And so the first one, we're going to do straight up math. We're just going to take Laplace transform, product, inverse Laplace transform, answer. But I very much want you to, and unsurprisingly, especially because we're using these computer tools, most students are very drawn to this approach. The problem is there's kind of two problems with this approach. The first one is, what if that doesn't work? And we're going to be pushing the symbolic tools that we have to the limits of what they can achieve. Not every Laplace transform has a nice closed form inverse. Okay, so that's the first problem, is what if that answer just doesn't exist? The other difficulty is, if we are always doing calculations, if my understanding of a system exists on the computer only, it becomes very difficult to reason about the behavior of systems and the consequences of making changes to those systems in my brain. And so I would like to avoid being so reliant on the computer systems, on insight into how these systems work, that I can only solve these problems on the computer. And so I am going to be spending quite a lot of time, okay, that's a very ugly brain, right? But I want you to be able to reason about this in your brain. That's a light bulb. Because you can only have ideas about things in your brain. That sounds like a bit of a totalitarian or a tautology, but just think about it, right? You have never made some kind of a connection, an aha moment, because of Google's database that is stored on their servers. Yes, you can search for it, and I'll be showing you the tools that I know of that make these calculations easier. But at the same time, if you want to be able to have design insights, in other words, if you want to say, oh, I believe that making the tank smaller will have this effect. And if you want to be able to do that in normal conversation like a normal human, those ideas will have to exist in your brain instead of on the computer. Okay, so let's focus on how we will do a simple calculation using the Laplace transform and the first kind of system that you guys have already started reading about, which is the classic first order system. Let's say I have a classic tank system and I'm trying to predict the level of that tank when this signal undergoes a step signal. And a normal person would say, what if this thing changes rapidly? Or what if this thing changes slowly from one place to another? Changes rapidly or quickly or whatever is kind of code for a step input. And we know that the Laplace transform of a step input of size A is A times 1 over S. Okay, so we know already kind of the input side of that equation. And if I Laplace that, so now we're going to write that in transfer function form. There you go. Okay, so this is now the transfer function for this tank system. I want to take a little bit of time just to show that every time you do a simple balance like this holds for energy balances, component balances, and mass balances. if the relationships are linear and there's only one of them, in other words, there's only one system that you're doing the balance over and there's only one balance, the result will always be a first-order differential equation. And if you Laplace transform that and identify the transfer function, the transfer function will always be what is known as a first-order transfer function. So the orders of these transfer functions work by naming the order of the denominator polynomial. And look at that. Okay, there was one derivative here. When I take the Laplace of a derivative, that's how I get an S. Okay? So derivatives go to S's. And so you can clearly see that if I have higher orders of derivatives, I'll get more S's. And you've done a couple of TUT problems where we started off with two linear first-order differential equations. When we plug those into one another, we end up with one second-order differential equation. And so, as a very general rule, the number of times that you have derivatives in your modeling equations translates to the number of S's that you'll have, or the order of S that you'll have in the denominator of the transfer function. That every time I see a derivative in the time domain, that's going to translate to an S in the Laplace domain. And when I rearrange that, that's in general going to end up below the line in the transfer function. Now, we're going to write this transfer function in a standardized form. Now, solving this for a unit step input is as simple as taking that, and remember now I'm trying to find h of s. So if h of s, and if this is g, right, I can write h of s is g of s times f in of s, and remember we already figured out that that's going to be some constant times 1 over s. So let's avoid confusion with the surface area of the tank and just call this thing something else. Let's call that beta. And so now we know that the h of s is equal to k tau s plus 1 times beta over s. And now you'll start seeing the logic of the table, right? Because notice that we started off with this k, but now we actually have a new constant of multiplication. And I prefer to think of these as being stacked, right? So I prefer to think of this being, well, there's a k beta as a thing on its own by itself. And then there's this form, tau s plus 1 s. And that's the part that has the dynamics in it because it has s's in it. Now I have to go and look at the table and find out what the inverse of that transform is. I will find that the inverse of this thing is 1 minus e to the minus t over tau. So that's the inverse that I will find if I look in the table. And you, like me, will learn this inverse because it's like the stock of first order systems. I expect you to be able to write down that inverse directly. So this is h of t. Does everybody see how I got there? Because I looked at this part and said, okay, that inverse corresponds to that time domain function, and you can look that up in the table. And then I said, okay, the gain part, I just multiply by whatever the coefficient is that I need there. Is this making sense to everybody? So this is the process. So that's the math, and you can do that. Trust me, once you've committed a couple of these standard inverses to memory, you will be faster using your brain than SymPy on these. Initially, go with SymPy, but obviously, like just writing down the answer from memory is usually easier than typing at all. Let's just look now at how that system behaves. Now, I'm leaving out, because this is purely algebra, I'm leaving out the part where I'm mapping between these two. Just let me know on Slack if you feel like I need to record a separate video on coefficient matching, but basically, if I ask you, if I say, well, these are both g of s, okay? G of s is equal to k over tau s plus 1. It is also equal to 1 over a s plus k, right? You tell me what is k and what is tau. This is not a dynamics problem. It's a coefficient matching problem. It's an algebraic problem. It's something that you will grapple with all the time, because obviously you won't get stuff in the standard form. Also, just to avoid any confusion here, these are different k's. So that's a different k from that k. Okay, just make sure you draw a distinction. Right, so what do these responses look like? And I'm going to show you how these parameters affect the response. So what you're seeing on this curve over here, the brown curve, is that is the step response. So in other words, that is the graph that gives us the answer to the question that we asked of this tank. In other words, this is what will happen to the level of a tank, how it will change from its initial position, because remember, we're working in deviation variables. Even though it starts at 0, that doesn't mean the tank is empty. It means the tank is wherever it was when we started. So there's a whole lot of assumptions built into this graph, right? When I'm drawing something like this, I would write the time of that, or I would write the value of that as 0 in deviation variables. And as a separate problem, you'd need to figure out what exactly the steady state was. So nowhere in the Laplace math that I've done here have I gone to the trouble of finding out what that initial condition was. And those are separate problems.